So let us consider this example. So suppose you have a random variable whose probability mass function is given by this e to power minus lambda, lambda to the power x by factorial x, if x is in 0, 1, 2, so on, and suppose this is 0 otherwise. One can easily check that this is a proper probability mass function. Now here lambda greater than 0 is a given constant. So clearly here support is 0, 1, 2, so on, which is this. I look at mxt, which is expected value of e to power tx, which is same as summation x equal to 0 to infinity. I am summing over sum e to power tx into the probability mass function over Sx. Probability mass function over Sx is equal to e power minus lambda, lambda to power x by factorial x. So e to power minus lambda comes outside. Then e to power tx lambda power x is common, so that becomes lambda et to power x by factorial x. Now once you do that, this whole quantity is nothing but expansion of e to power lambda e to power t, and that is what I do over here. So this is e to power minus lambda into e to power lambda e to power t, because this is an expansion of e to power lambda e to power t. So this becomes e to power lambda e to power t minus 1. Now this happens, this is finite for any t belonging to R. So moment generating function exists for any t in R. So in particular, it exists in a neighborhood of 0. So thus mu r prime is finite for every r belonging to 1, 2, so on. So I can get my moments now using the moment generating function. So let us try to see the mean and variance. So I try to look at psi xt, which is log of mxt, which turns out to be lambda e to power t minus 1, because mxt you have seen is nothing but e to power lambda e to power t minus 1. So log of mxt is nothing but lambda e to power t minus 1. So if I look at psi x1t, turns out to be lambda e to power t. Psi x2t also turns out to be lambda e to power t. So psi x10 is same as psi x20, which is same as lambda. So this says that expected value of x is same as variance of x is same as lambda. So this is a distribution for which the mean and variance both are same, and they are same as lambda. Now note that I had also said that one way to get moments is differentiate either the cumulative generating function or the moment generating function. Other way is look at the Maclaurin series expansion of mxt. So I am trying to look at that. Mxt is nothing but, I try to look at expansion of this. Expansion of e to power x is 1 plus x square and so on. So this becomes, expansion of this quantity becomes 1 plus lambda e to power t minus 1 plus lambda square e to power t minus 1 whole square by factorial 2 plus lambda cube e to power t minus 1 whole cube by factorial 3 and so on. So let me call this quantity e to power t minus 1 as s. Then this becomes 1 plus lambda s plus lambda square s square by factorial 2 plus lambda cube s cube by factorial 3 and so on, where s is nothing but e to power t minus 1, which is, if I expand e to power t, this becomes t plus t square by factorial 2 plus t cube by factorial 3 and so on. 1 gets cancelled because e to power t expansion would have 1 plus t square by factorial 2 and so on. So you get this. So what I have to do is, from here I have to collect the coefficients of t to power r by factorial r for various values of r. So let us look at what would be the coefficient of t. So coefficient of t, if you look at, when you consider s square, the minimum power of t would come is t square. So that means t can come only from s, which is lambda times this quantity. So the only t is coming is lambda. So coefficient of t is lambda. Now let us look at coefficient of t square. T square, note that, will not come from s cube onward, because s cube, the minimum power would be t cube. So it will come only from lambda s or lambda square s square by 2. So let us see what it comes from lambda s. From lambda s, it comes to be lambda by factorial 2. That is the thing. Then it's square. It's square, when you do it, it would come t square, and then the power would come t cube. So that means only the coefficient of 1 would come, and that would be lambda square by factorial 2. So that means coefficient of t square by factorial 2 turns out to be lambda plus lambda square. Now similarly one can get the coefficient of t cube by factorial 3. Note that t cube would come from the first term, the second term and the third term. The first term, the coefficient of t cube is nothing but lambda by factorial 3. Lambda by factorial 3. From the second one, it is s square. So s square would make it t square t4. The only thing can come is twice times cross product of this. So that becomes twice lambda square by factorial 2. And then from here, s cube, only the first term would come t cube, which is lambda cube by factorial 3. So you can get the coefficient of t cube by factorial 3 by multiplying factorial 3 over here. So what you finally summarize this as this. mxt is 1 plus lambda t plus lambda square plus lambda square. That was the coefficient of t square by factorial 2. Coefficient of t cube by factorial 3 turns out to be this. Just now we saw that. So expected value of x is coefficient of t in mxt, which is same as lambda. Expected value of x square is coefficient of t square by factorial 2 in mxt, which is lambda plus lambda square. Expected value of x cube also you can get, which is coefficient of t to power cube by factorial 3 in mxt, which is nothing but lambda cube plus 3 lambda square plus lambda. Actually this should not be factorial 3 over here. This is only t cube, because that is what we saw. So lambda by factorial 3 plus 2 lambda square by. So that is why you'll get this. So variance of x turns out to be, so you can check these calculations. There may be possibility that there may be small calculation error, but the idea is clear. So if you, what you have to do is you have to find out the coefficient of t cube by factorial 3 in mxt. So variance of x turns out to be expected value of x square minus expected value of x whole square, which turns out to be lambda plus lambda square minus lambda square, which is same as lambda. Now let us consider another example. Let x be a random variable of absolutely continuous type, and suppose its PDF is given by this, where lambda is a positive constant. You need lambda to be positive, otherwise this will not be a PDF, because this will not be non-negative quantity. So look, if I look at any neighborhood of 0, then, and I integrate fxx, I get a positive quantity. So that means my support would be 0 to infinity. Whereas if I look at any quantity less than 0, then I can always find a neighborhood where density is 0. So if I integrate density in that neighborhood, I get 0. So that point will not be in support of x. So anything x less than 0 is not in support. X greater than or equal to 0 in support, because the moment I look at neighborhood of 0, the point on rights would come, and if I integrate this PDF, I'll get a positive quantity. So Sx is 0 to infinity. So mxt is expected value of e to power tx, which is same as minus infinity to infinity, e to power tx fxx dx. But my density is 0 if x is less than 0. So it is contributing only when x is greater than 0. So that becomes x equal to 0 to infinity, and this becomes lambda e to power minus lambda x for x greater than 0. So lambda comes outside, e to power minus lambda x plus lambda t, and that is how this combines with this, and you get e to power minus lambda minus dx. Now note that for this integral to be finite, this coefficient has to be positive. If this is not positive, it is negative, then this may explode. Even lambda is equal to t, it gets exploded, because you get 0 to infinity dx. So that means for this integral to exist, you should have lambda greater than t, or t less than lambda. And then this quantity becomes, if you look at this whole integral, this quantity becomes, lambda was already there, lambda upon lambda minus t, which is nothing but 1 minus t by lambda to power minus 1. And that is what is done over here. But for this to exist, t should be less than lambda. So in fact, 0 was here, lambda was here, so I can always take that neighborhood of 0 to be lambda to minus lambda, because it is existing for any t less than lambda. So it will exist for t belonging to minus lambda to lambda. So moment density function exists in a neighborhood of 0, so thus moments of all orders exist by a result which we did. Let us try to see how do I get the moments? One way is you expand it to Maclaurin series, which is very nice for mod of t by lambda less than 1, or you differentiate it, and that is what I do. So your mxt is 1 minus t by lambda to the power minus 1, and I have taken t to be minus lambda less than lambda. So mod of t by lambda is less than 1, so I can expand this in geometric series. So this turns out to be 1 plus t by lambda plus t square by lambda square plus tr by lambda to the power r. What is the mu r prime, which is the coefficient of t to the power r by factorial r in Maclaurin's series expansion of mxt. So I divide it by factorial r and multiply. So the coefficient of t to the power r by factorial r is nothing but factorial r by lambda to the power r. So I have got the rth moment, which is nothing but factorial r by lambda to the power r. Other way to do is you differentiate it once. So mx1t turns out to be minus 1, 1 minus t by lambda to the power minus 2. Then minus will come over here, and 1 upon lambda would come. So this is the derivative. I differentiate it now this once, so I get mx2t, which is 2 by lambda square, 1 minus t by lambda to the power minus 3. If I keep on doing it, if you differentiate it r times recursively, you get factorial r by lambda to the power r, 1 minus t by lambda to the power minus r plus 1 for t between minus lambda to lambda. And to get the rth moment, I put mxr0. So put t is equal to 0. This goes away, so you get factorial r by lambda to the power r. So you can see both differentiating moment generating function and expanding it in Maclaurin series turns out to be very handy in determining the moments. Now let us consider this example, which will illustrate that moment generating function may not always exist in a neighborhood of 0. So for t greater than 0, I look at what is mxt, which is expected to be e to the power tx, which is same as minus infinity to infinity, e to the power tx, fxx dx. E to the power tx is this, fxx is this. Now note that this whole quantity is non-negative, and if you are integrating in minus infinity to infinity, so what I do is now I integrate it over a smaller range, which is 0 to infinity. Since the function is non-negative, I will get a smaller quantity because I am integrating a non-negative function over a smaller range. So this would be greater than or equal to 1 by pi, 0 to infinity, e to the power tx upon 1 plus x squared dx. But you know that e to the power y is always greater than or equal to y for every y greater than 0. Now here t is positive, x is positive, t is positive, x is positive, so e to the power tx would always be greater than or equal to tx. So that is why this whole quantity would be greater than or equal to 1 by pi, 0 to infinity, tx upon 1 plus x squared dx. If you take t outside, this becomes t by pi, in fact t by 2 pi, and then it is a derivative of that, so log of 1 plus x square, 0 to infinity, and this becomes infinity. So mxt is infinity for every t greater than 0. So that means you cannot find any neighborhood of 0 where mxt is finite, because you have shown that mxt is infinite as long as t is greater than 0. So mxt is not finite on any interval minus h to h greater than 0. So in this case, I cannot apply that result. I cannot say that moments of all order exist, and you can get those moments by differentiating the mgf. In fact, we have seen before that here expected value of x does not exist. This we saw in the last module. So although in many situations moment generating function exists, but there would exist some very peculiar situations where moment generating function may not exist. So you cannot get the moments through moment generating function approach. Now before I proceed, let me give you some take home problems. So let x be a random variable with probability mass function as this. Now for this to be a proper probability mass function, this series has to be convergent, summation 1 upon x to the power p. So for that p has to be greater than 1. And of course Cp is the normalizing constant. So that the mgf of x is not finite on any interval minus h to h. One way to do this would be prove it by contradiction. Suppose moment generating function is finite on some interval of the type minus h to h. then movements of all order exist, and then you show that there will be few movements for which will not exist for this PMF. Now let us consider another problem. Let X be a random variable with MGF given by this. Find probability mod X greater than 0 and the PMF of Y is equal to X square. One way to do this would be try to identify the random variable for which this is a MGF. Now once you have identified the random variable and its distribution, getting these things would be straightforward. So I have given you a hint for this problem. Now let me give a brief summary of the things which I will be doing in the next module. In the next module I will give a definition of two random variables having the same distribution. So two random variables X and Y are said to have the same distribution, and we write down that as X is same as Y in distribution if they have the same distribution function. So certainly if they have the same distribution function, they will have the same PMF and they will have a same PDF. Now note that when I say that X is having the same distribution as Y, this means that their probability distribution is same, but X may not be the same as Y. So it is saying as, for example, let us look at two different populations. Let us say population of students at IIT Kanpur and population of students at IIT Bombay. And I am interested in their heights. So X is a random variable representing the height of students at IIT Kanpur, Y the height of students at IIT Bombay. The distribution may be same, but saying that as a random variable X and Y are same, that is equivalent to saying that the two populations are same, which is not correct. So this is a situation where, this is a typical example where you saw that the random variables may have the same distribution, but they may not be the same. So in next module we will study properties of random variables having the same distribution. So that was all for this module.